So far, all of the antenna that we've considered in this labs are linearly polarized. So for example, if we had a dipole antenna and it was horizontally polarized, it would make sure that the transmitting antenna that's illuminating this dipole antenna is also horizontally polarized to have polarization match. When we had one of them was horizontally polarized, the other one was vertically polarized, we would get very small signal. So this is one of the disadvantages of a linearly polarized antenna. When you don't know when the polarization that's illuminating you would be, for example, vertically polarized or linearly polarized or 45 degrees slant. So essentially, if you don't know that, and this could happen, for example, in satellite communication, then circularly polarized antenna can provide an advantage for us. For example, this is a helical antenna considered in the LabVolt student manual. And if you look at this, it consists of a few parts. So this is essentially the feed that goes here. This is the ground plane. So this I don't know how good you see that, but that's the ground plane. And then you have the helical shaped wire inside here. And this is essentially the radome. We've covered radome in a different lab, and that stands for radar dome, which is used for protection of the antenna. So we have our radome, we have our helical antenna, and it's backed by a ground plane, and that's the feed that's coming. So this in fact can provide circular polarization for us. And when it comes to circular polarization, we have another thing called sense of rotation. As you learned in the class, it can be right-hand circularly polarized or RHCP, or left-hand circularly polarized as LHCP. In this lab, we're gonna study both of them. We're gonna have both an RHCP and LHCP helical antenna. So RHCP, we sometimes refer to that as CW clockwise. The LHCP would be counterclockwise. So the way to figure out the polarization, the sense of rotation of this antenna is that you're gonna be looking at this antenna, and then I'm gonna use my fingers so that when I'm gonna rotate my fingers in the same way that this winding rotates. So if I do that, and you see that with my right hand, now I have thumb in the direction of main beam, which I'm going to discuss right now in the axis of this helical antenna. So because now if I rotate it in the same way that this rotates, my right hand can do that, and this is going to go to the direction of the main beam axis of the antenna. So in this case, this is right hand circularly polarized. If I bring another antenna that I need to use my left hand to do the same job, so that the left hand, when I'm rotating the fingers, is in the same direction as the winding, and then my thumb is in the direction of the axis, that essentially would be left hand circularly polarized. So the one that I have in my hand right now is right hand circularly polarized. So this is essentially introduction to helical antenna. One thing to note here is that helical antenna has two modes of operation. So the one that we don't consider in this lab, one of them is normal mode, essentially. So if you have a helical antenna, if the main beam is normal to the helical antenna, that's essentially normal mode. So imagine, for example, this is your antennas, and then this would be the direction of the main beam, this direction. Similar to, for example, dipole, that you have the main beam in this direction. So that's the same thing. That would be the normal mode. For normal mode, you want the size of this antenna in terms of diameter of turn and the length of the wire be very small compared to the wavelength. So in this case, that's not the case. I'm operating at 10.52 gigahertz, so my wavelength is close to 3 centimeter. And if you look at the length of this helical antenna, it's not much smaller than wavelength. So this is not normal mode. When we go to the other mode, Before going to the other mode, let me also mention that normal mode is called also broadside mode because it's perpendicular to the axis of the antenna. The other mode is essentially axial mode or end fire mode. So the direction of the main beam would be along the axis. So that would be the direction of the main beam. That's why we call it also end fire. And remember, this is backed by a ground plane. So this essentially limits the radiation in the back lobe. So if it goes along the axis of the antenna, that would be my axial mode. For the axial mode, you essentially, before talking about axial mode, I have a plot of the helical antenna here. This is my coaxial cable, and then I use the inner conductor to create my helical antenna. This is my ground plane, and as you see, I have some turns, I have a spacing between turns, I have the diameter here. And so if you look at this antenna right now, the circumference of each turn, if this is the diameter d, would be pi times d. That's the circumference. And for the helical antenna to work in the axial mode, you want this circumference to be about one wavelength, just approximately one wavelength, maybe between 3 divided by 4 wavelengths to 4 divided by 3 wavelengths, roughly one wavelength. So we want the circumference to be about one wavelength, and we would like to have some number of turns. We don't want to limit ourselves to just maybe one or two. We want to have some number of turns so that the length also, you have a reasonable amount of length compared to wavelengths. So that's the way that you get to the end fire mode that we're going to have in this lab. That would be the one that we have. And in that case, it might come a little bit surprising to you that why all of a sudden, if this circumference in one wavelength and the length is now relatively larger than wavelengths, now what's going to happen that all of a sudden I go from normal mode, where the main beam is in this direction, to the axis of that. I mean, it's beyond what I want to explain in this part of the lab, the detailed reason, but it shouldn't come completely as a surprise for you. And the reason is, if you remember, in any way, these are somehow like loop. So not exactly, but you can think of it as loop. And if you remember the loop antenna of circumference one wavelengths, we had a situation that when the loop was small, the main beam was in this direction. After it became circumference of one wavelength, the main beam went to the axis of the loop. So my point here is not to create one-to-one correspondence between these antennas, but to tell you that is not as surprising as we might think. But the thing that's important in the explanation and the understanding of this is to understand that this is now circularly polarized. So we couldn't get that from the loop antenna that we studied previously. So one thing that's also useful to note here when it comes to this type of helical antenna is that if you, for example, if you open one turn of this, so let's see what's going to happen. So this is essentially one turn. So let's call it L naught. This is the length of one turn. So if I open that, so I'm going to open this circumference D, so it becomes pi D, and this S remains here, and this becomes pi D, and then this L naught, of course, becomes from here to here. So this is essentially, if I open one turn, I get this triangle here. And the important thing is this angle. This is called pitch angle. So this is the pitch angle, and this is, I mean, for example, could be 12 degrees, 13 degrees, this type of number. So as you see, consequently, L naught and pi d would be relatively close to each other. So, and you realize that if alpha goes to 0, if alpha becomes a smaller and a smaller and a smaller, this S becomes a smaller and a smaller and a smaller. It becomes almost like you have not that many number of turns in loop. And if alpha becomes bigger and bigger and bigger, So spacing becomes larger and larger and larger, and it almost going so that you have like a wire antenna goes like almost like a monopole antenna. So this is, but for helical antenna that we have, this is roughly 12 degrees and 13 degrees. For example, the one that we have right now is D is 8.4 millimeter. So, and the circumference is roughly 28.56 degree. The frequency of operation that we have is 10.52 gigahertz, and the wavelength therefore is 28.52 millimeter. Now, if you compare the circumference here with the wavelengths, you see that the circumference and wavelengths in this case are relatively similar. So, and then you can understand that this is the axial mode that we are considering in this step. It's not normal mode, because otherwise it would have been much smaller compared to wavelengths. So that's essentially a couple of points regarding the helical antenna. But the most important thing that we want to see in this lab, we want to see that if we rotate our linear polarization by 90 degrees, what's going to happen to the pattern of the helical antenna. And we also want to calculate the gain of the helical antenna. We're going to also do that using a standard gain that we had in a different lab. The other thing that's interesting, and we're going to do at the end of this lab, would be to find the axial ratio of this helical antenna. So if everything is perfect, if you remember, for perfectly circularly polarized antenna, axial ratio is 1. So if I have a perfect circle like that, the major axis to minor axis would be exactly equal. The ratio would be 1. So axial ratio end up to be 1. But if it's not perfectly circularly polarized, I may get a number bigger than 1. So I guess you remember that the axial ratio is from 1 to infinity. So if we go closer to infinity, we're becoming more linearly polarized. If we're getting close to 1, we're getting more close to perfect circular polarization. And between, you can call it elliptical polarization. So these two examples, circular polarization and linear polarization, would be a specific case of elliptical polarization, where one of the axes in the case of linear polarization vanishes, and in the circular polarization, the two axes becomes identical. So let's go step by step to the lab and see our experiment. Okay, before starting our test with the helical antenna, we're going to do a measurement using the smaller horn antenna that we know its gain at 10.52 gigahertz. So essentially, we want to use this as a standard gain in this experiment. So as LabVault student manual suggested, we keep the distance aperture to aperture 1.5 meter. In this case, we use E-plane measurements for gain reference. You could do H-plane measurements too. If you remember, the peak of the E-plane and the peak of H-plane should match. So theoretically, if I measure E-plane and I get a maximum signal level, or MSL, at a certain dB, the H-plane should have the same thing. And that's essentially my reference. So based on that, it doesn't matter which one you measure, but you just need to be careful that if you mount that in the E-plane configuration, you need to make sure that this is polarization match. So right now, both of them are horizontally polarized. So that would be my reference. So one thing you should also be careful when we getting to the point that we want to calculate the gain of the helical antenna is the polarization loss factor. When these two antennas are now polarization match, essentially I don't have any polarization loss due to polarization mismatch. But remember, when you do helical antenna measurements, that's a circularly polarized, and now we excited with the same, of course, horn. We illuminated with the same horn, and that's linearly polarized. So right away, we're going to have 3 dB polarization loss factor. So you need to take that into account when you are calculating the gain of the helical antenna using using a linearly polarized antenna like this. So now we can start our measurement. So I need to turn on the RF signal. The RF signal is on, and then I need to start the software. So the software is initializing, and now I need to press data acquisition. So when I press data acquisition, I'm at the saturation level. So I'm just gonna stop the measurement, and I'm gonna apply some uh, attenuation in the data collection software. And so right now it is at 18 dB attenuation. I'm just gonna check what would be the maximum signal level using this attenuation, and then decide if that's a good attenuation level or not. So unfortunately, right now I'm not at the maximum, so that I cannot see that. I want to be around -2, -3 dB in terms of the maximum signal. If I apply too much attenuation, then I might miss some of the details. Now, when I did that, and using this 18 dB attenuation, right now, if I take a look at that, my maximum signal level right now is at -3.07 dB. So that's a reasonable maximum signal level. If it was, for example, -10 dB maximum signal level, I will reduce some attenuation. So -3 as a maximum signal level is acceptable. So I'm gonna accept that as my attenuation. Then I'm gonna now uh, show you the screen of this to see what is the pattern that we have, what is the maximum signal level. And then let me turn this off. And then we're gonna use this as our reference. Remember, we don't really need to perform pattern measurements for our standard gain. We just need the maximum signal level. But then if we don't want to do pattern measurement, we need to make sure that it's positioned in a way that we are at the maximum signal level, and then we record that signal. But because we don't know exactly if it's completely aligned with the transmit antenna, we do one pattern measurement to make sure that we have the maximum signal level corresponding to that. So now that is done, let's go check out our pattern, and then we're going to continue with the helical antenna. Okay, we have now our smaller horn antenna, which we treated as a standard gain for this example, mounted on the receiver mast, and we have the larger horn antenna transmitting. Both of them are positioned horizontally, so in fact we are measuring E-plane of our smaller horn antenna. So let's start the data acquisition. Also remember that, as I explained in the previous video, I applied 18 dB attenuation in this case. So let's see what would be the pattern. Now we go now to back lobe of our smaller horn antenna. And as I mentioned also in the previous video, what we really care for this pattern is its maximum signal level, because this is the maximum signal level that we say correspond to the gain of the smaller horn antenna, that we know it from a different experiment. So this is essentially that maximum signal level that matters to us. Okay, so this is our E-plane of the smaller horn. I'm gonna store it under E-plane, and let me complete my. So now I have my pattern, as you see, and the maximum signal level that I have is at -2.86, as you see here. So I probably would have been better if I saved it under document 1, which is empty right now, but it's under document 2 right now. which is fine. I'm going to rename it later on to the standard gain for this example. So this is my pattern, and it is, as you see, it's minus 2.86 maximum signal level. So just to be consistent, we're going to bring it maximum signal level to 0. So now this is my pattern. So in a sense here, the conclusion is for a signal level of minus 2.86, I have a certain gain. Now, if I measure helical antenna, how would I calculate the gain? So this is what you need to work on. So let's go and start our experiment with the helical antenna. We have now mounted our right-hand circularly polarized helical antenna on the mast, as you see. So this is essentially the antenna that we have over there. So this is right-hand circularly polarized. If I look at the winding of this helical antenna from the feed point here, if I rotate my right hand finger in the direction of the winding, my thumb would be in this direction. So we call it right hand circularly polarized or clockwise. So CW. So this is the way that is mounted. And the transmitting antenna is horizontally polarized. We have a horn antenna, so essentially this is polarized in this way. If you can see the aperture of this waveguide and the transition to aperture of the horn and the transition to waveguide, you can easily see that the polarization is horizontally polarized. So we have a situation like that. The transmit wave from the horn antenna is horizontally polarized. This antenna here, the receive antenna, is expecting circularly polarized. So there would be a polarization loss factor between linearly polarized and circularly polarized, and it's going to receive. So this would be the measurement that I'm going to do right now. And to do the measurement, let's go and start the RF power. So I'm going to start the RF power, and I'm going to start the data collection. So as you see, the antenna under test is rotating right now. So this would be essentially the back lobe. And now we are going again to our main lobe. So now the measurement is done, and we can go check the measurement. Okay, we have now one of the right-hand circularly polarized helical antenna mounted as the receiving antenna. We still have our horn antenna as the transmit, larger horn antenna. At the transmit, the polarization of the transmitting antenna is horizontally polarized, and we are illuminating our helical antenna. So let's see what sort of measurement we're gonna get from this. So let's start our measurement, and see what we will have. So this helical antenna that we have, as we noted earlier, is backed by a ground plane. So right now we go to the back of the antenna. So this is the back lobe of the antenna. And so we are now again going to the side of the antenna and approaching the main lobe of the antenna. So the measurement is now done. I can store it under, this document here, and to finish my storing. Okay, I have it right here. Okay, so so this is the pattern that I got. If I want to be consistent, I can rotate the maximum signal level so that it's 0 degrees. So this is the pattern that I get. So now the question here is about gain. I mean, I want you to think about gain for a second. So when you comparing, remember that in the previous case, the maximum signal level, which is for the smaller horn antenna, was obtained under perfect polarization match. Here, your antenna under test is circularly polarized, but then the transmitting antenna is linearly polarized. So then you need to take that into account. So of course, you're going to lose some signal because of this polarization mismatch. So take that into account. Now, if we look at our half power beam widths here, you see that the one that we measured for helical antenna is 26.03 degrees, and for the smaller horn antenna we have very close 30.57 degrees. So right now this is our measurement. In the next part we're gonna rotate our transmitting horn antenna by 90 degree, and we're gonna repeat this measurement. Okay, now we're gonna see one of the main advantages of circularly polarized antenna. Assume that, for example, uh, in the previous case, we had a dipole antenna. So this is linearly polarized, and right now I've kept it in a way that is horizontally polarized. As you remember, the polarization of the horn was linear, horizontal polarized. So these are I have polarization match. Now, if I keep my dipole antenna exactly as this, it's still horizontally polarized, but then I'll go and rotate the polarization of my horn antenna by 90 degree, just like that. So now the polarization of the horn antenna is vertically polarized, but then this is my dipole antenna, linearly polarized horizontally. So this is vertical polarization, this is expecting horizontal polarization. Theoretically, I should receive nothing. Of course, I have some cross polarization, and I receive something. You've seen that in a different lab, that you still receive something, but much smaller than the when you have polarization match. But now we're gonna see that circularly polarized antenna doesn't work like that. So to check that, now we've rotated our transmitting antenna 90 degree, but I'm not gonna touch my circularly polarized helical antenna. So that's as in previous case. So if it was linearly polarized, you expect much smaller signal. But now you'll see that the signal level is not exactly, is approximately at the same level. Now, this would be an advantage, because if you don't know what is the direction of linearly polarized coming to you, you still ensure that you're receiving something. Now, you should justify that based on the equation and mathematics, that why if I change it by 90 degree, you are still going to receive pretty much the same thing in terms of the maximum signal level. So now I can start the measurement, but you already seen the rotation of this, nothing will change. So let's go, and I'm going to perform the measurements, but then we're going to go and see what we're going to be receiving in the lab vault software. Okay, we have now rotated our transmitting horn antenna 90 degree. So in fact, now we've changed the polarization of the horn to vertical polarization. We haven't touched our helical antenna. So if the helical antenna was a linearly polarized, in this case, we're gonna receive very minimal signal, because if the helical antenna was like a dipole antenna, and we all of a sudden rotate the transmit antenna by 90 degree to go from copole to cross pole, then we had theoretically zero signal. But this is a circularly polarized antenna, so you'll see if when you have a circularly polarized antenna, what's going to happen. So again, to repeat that, We have not touched our helical antenna, as in the previous case, the same, but we rotated the polarization of the transmitting antenna by 90 degrees. And we're gonna start our measurement again. So what we care the most in this case is to look at the overall shape of the pattern and the maximum signal level as well as half power beam width. So if you look on the right column, the maximum signal level of the previous case was minus 6.28. Now what would be the maximum signal level in this case? The half power beam width in the previous case was 26.03 degree. What would be the half power beam width in this case? So now the data collection is done. Let's store that. So you see here, I'm storing it under H plane, and the reason I'm storing it under H plane is because the horn antenna is essentially in a H plane case, but E plane and H plane in this case for the helical antenna uh, is not relevant. Is it? We just go by the E plane and H plane of our horn antenna. So now this is the new measurement. To be consistent, I'll go to 0 degree for the maximum signal level. And as you see, we see something very interesting, that the maximum signal level, although we haven't touched our helical antenna, is almost identical to our the previous case measurement. So you have minus 6.28 maximum signal level in the previous case. Now you have minus 6.33. So that essentially means with the change of polarization of the transmit antenna, the maximum signal level did not change much. Now you need to explain why this is the case. Also look at the half power beam width. The change is not much. In the previous case we had 26.03 degree. Now we have 22.89 degrees. So that essentially shows one of the main advantages of the circular polarization, that when you don't know the polarization of your transmit antenna, if it's, you assume your transmit antenna is linearly polarized, and due to some issues, for example propagation through ionosphere, it might, the polarization may rotate a little bit, then then would then this type of antenna would be advantageous. So that's our experiment for this case. Now let's move on with the next experiment. Okay, we just performed measurement with our right-hand circularly polarized helical antenna. The lab volt system comes with also a left-hand circularly polarized antenna. So we're going to repeat whatever we did so far with our left-hand circularly polarized antenna, or CCW, counterclockwise. So to just repeat what I said earlier, this is essentially our right-hand circularly polarized that we have right now. So if I rotate my hand, my fingers of right hand in the directions of the winding, I'll go to the main beam that I have in the axis of the helical antenna. So as you remember, these antennas are working in the axial mode. So this is the direction of the main beam. So, and the reason they are working in the axial mode, not normal mode, is because the circumference is close to one wavelength, and the length is also greater than wavelengths. So it's not a small antenna. So that's what we explained earlier. But the main thing here is that these, if you rotate your fingers in the direction of the winding, so your thumb is going to show the direction of the main beam. Now, if I have this one, the other one that lab would provide, this one, the winding is reversed. So this time, if I want to go to the direction of the main beam with my thumb, I need to rotate my left hand finger. So if I do that, then I'll go this way. So the rotation of my left hand fingers is consistent with the rotation of the winding here. So that would be my the left hand circularly polarized because I need to rotate my left hand. So that would be essentially the other antenna that we try. So in the first case, the electric fields, if that's electric fields are going to rotate like that, in the new case, they're going to be reversed. They're going to be rotating like that. For a linearly polarized, if it's vertical, it's going to be like this, or horizontal, it's going to be like this. But in this case, these are circularly polarized, so it's either clockwise in this direction or right hand circularly polarized, or counterclockwise or left hand circularly polarized. So now what I'm going to do, I'm going to mount the left hand circularly polarized right now instead of this one, and perform again measurements. And to be consistent with the order of measurements, I'm going to make sure that my horn antenna is horizontally polarized in the first experiment, and then I'm going to make it vertically polarized. So the first measurement that we're going to do would be antenna under test, left hand circularly polarized helical antenna. The horn would be horizontal polarization. Next measurement, we're not going to touch our left hand circularly polarized helical, but we're going to rotate the polarization of the horn antenna so that it becomes vertically polarized. And we're going to have two data acquisition. Okay, as noted in the previous video, we are now moving to measure the left-hand circularly polarized helical antenna that has been mounted. So our antenna under test is left-hand circularly polarized. The horn antenna is now also horizontally polarized to be consistent with the order of previous measurement. And now we're gonna start performing our measurements. So again, remember that the antenna under test is circularly polarized, in particular left-hand circularly polarized, but the transmit antenna is horizontally polarized. So you would know from the course that we have a polarization mismatch, and when you want to calculate later on the gain of this antenna based on these measurements, you need to take that into account, that in our gain reference measurement we did not have any polarization loss factor because we had complete match between the transmit and receive antenna, whereas in this case we get a little bit of difference. Okay, now our measurement is done. So I'm just gonna store this, and now I can also rotate my measurements at set maximum signal to 0 degrees like that, and this would be my measurements. It seems I have a bit of problem in my measurements, especially a little bit of ripples I have, especially if you look at the main lobe. I have some ripples. I could probably go, and because when I did that, it's not identical to the previous measurement, so I moved around a couple of things. I maintained the same distance though, but we have a little bit of problems in the main lobe. For now, let's keep it like that and perform our calculation based on this, and then we may come back to it and figure it out at a different time. But what you see here is that the maximum signal level compared to the case of right-hand circularly polarized increased. For the right-hand circularly polarized, the maximum signal level was minus 6.28, whereas right now I'm at minus 4.19. So this is a difference that I have. Now, in the next measurement, what I'm going to do, I'm going to rotate my horn antenna, keeping the antenna under test exactly the same. So let's rotate the horn antenna 90 degree and then perform the measurement. So I'm just going to do it right away and rotate my horn antenna 90 degree to make it vertically polarized. Okay, now I've rotated my horn antenna 90 degree, and I'm ready to perform my measurement. So the horn antenna is vertically polarized right now. The antenna under test is the same as before. The reason I'm waiting a little bit is that when I rotated my horn antenna, uh, due to this rotation and putting it back, I've got a little bit of vibration in the transmit mast. And if I get vibration in the transmit mass when I'm collecting my pattern, I'm gonna have ripples in the pattern. So I thought I'll just talk a little bit so that vibration decays, and then I start my measurements. Now it seems to be relatively okay, so I'm gonna perform my measurement right now. So one thing that you may notice right away is that it seems I'm not at the same maximum as the previous measurement that I had. So to see that even better, maybe I should uh, later on remove the other patterns and just keep the patterns that we are talking about, which is for the left hand circularly polarized antenna. So let it finish, and then I'll come back to it and check this to see how consistent I am. So I'm gonna store that also, and so now I'm gonna hide other measurements that we had. So this is only the left hand circularly polarized. Now I'm gonna rotate this at to 0 degrees, and if you look at that, it's actually not bad because in the previous measurement, in the previous case, my maximum signal level was at minus 4.19, but now I'm at minus 4.62. So that's the pattern that I've got. So ideally, the maximum signal level should be exactly the same, but here I have a bit of discrepancy, and as I mentioned, the previous data collection had a bit of problem. If you look at it like now, this ripples in the main lobe is not very good. So ideally, we should have repeated that to fix the issue. But so so right now I have this pattern which is relatively the same. So my suggestion would be, when you are calculating the gain, for gain calculation, let's rely on this signal level that's for the left hand circularly polarized. That means use the signal level of minus 4.62 instead of minus 4.19. So that's our left hand circularly polarized. I can bring my uh, this was for the horn antenna, so this was the for the right hand circularly polarized. That was, in terms of signal level, is a slightly lower. So now that I'm a slightly lower uh, for the right hand circularly polarized, you could guess that the gain of the left hand circularly polarized antenna here, it should be more than the gain of the right hand circularly polarized antenna. And I can also bring the horn antenna. That was my horn antenna. And in horn antenna, when you look at the horn antenna, you might want to say immediately that maximum signal level is higher, so probably its gain is higher. But this conclusion is not necessarily correct. As I mentioned, the horn antenna does not have that polarization loss factor issue that I have with circular polarization. So be careful of that when you're making your calculation of the gain. Now, if I again hide my previous measurements, I could look at the half power beamwidth that I measured for the left hand circularly polarized. When the transmitting antenna was horizontally polarized, half power beamwidth became 25.66. when the transmit antenna was vertically polarized, it became 21.21. And if you compare it with the half power beamwidth that I have for the right hand circularly polarized, it's very close. So you should compare 26.03 with 25.66 and 22.89 with 21.21. Okay, we have now measured our right-hand circularly polarized RHCP and left-hand circularly polarized LHCP helical antennas. We also had a standard gain measurements. Now you have everything to perform gain calculations for these two antennas. So as noted in the lab volt manual, there is also a formula that you can use to calculate the gain of the helical antenna. The lab volt manual gives the specification of the helical antenna. You can check it out in the student manual. And based on that, you can calculate the gain using that equation and see how much is different than our measurements. So that's one thing you should do. And the other thing that's very important, and I mentioned it a couple of times, when you do that, remember that in previous labs, whenever we did gain calculation using these measurements, we didn't have polarization loss factor issue. But here we have, because in gain measurements, in the standard gain measurements, we didn't have any polarization loss factor. But for the circularly polarized to linearly polarized, we have. And you already should know what is that value in terms of dB. So you need to add that to your calculation. Okay, so in the previous measurements, always the transmit antenna was horn antenna. In other words, always the transmit antenna was a linearly polarized antenna, and we were changing right-hand circularly polarized to left-hand circularly polarized for the receive antenna. Now we have a different situation. We have our transmit antenna as a right-hand circularly polarized antenna. The receive antenna or antenna under test is also right-hand circularly polarized. So both of them are actually identical, the two right-hand circularly polarized antenna of the lab volt. So we have these two antennas. There is, I mean, according to the manual, I have them separated by 1 meter. I put a book under the transmit mast to a little bit adjust the height, but it still is not perfect. But anyways, I mean, we could perform these measurements and be consistent at least when I'm changing the antenna. So in the first measurement, what I'm going to do is that right-hand circularly polarized transmit, right-hand circularly polarized I have on the antenna on the test side, and then we're going to see what would be our signal. So let's start our measurements and let's see what we're going to get. So I'm not going to show you the performing the measurements. You've seen it several times. This antenna is going to rotate 360, and we're recording the data on the lab volt data acquisition and management software. So I'm going to go in the next video directly to the software. Okay, right now we want to perform measurements when we have two right-hand circularly polarized antenna, one as the transmit and the other as the receive. Both of them are helical antennas that lab volt system provides. Now, so let's start our measurement. So if we start our measurements, we essentially get a signal right now, and something I also would like to mention is that uh, I have this I mean, of course our room is not an anechoic chamber, but remember that I also have cameras and things like that close to the measurement system that sometimes I forgot to remove. So I mean, in that way it's gonna make the room even more unsymmetric. So this is one thing that I have here. So let me store it, and so let me store this. So these are right hand circularly polarized, and I can also set the maximum signal level to 0, and I get this type of radiation pattern. So that's our first measurements. Now let's go to the second one. Okay, as you know, in the previous measurement, we had our two right-hand circularly polarized, one of them as the transmit, the other one as the receive. Now, what we're going to do is that we're going to get our left-hand circularly polarized, and we're going to replace it for the transmit antenna. So we're not going to touch our receive or antenna under test. We're just going to change that to a left-hand circularly polarized. Therefore, the transmit would be left-hand circularly polarized, and antenna under test would be right-hand circularly polarized. So let's do that. And so I'm just going to remove that. And have my left-hand circularly polarized antenna. So this would be my left-hand circularly polarized antenna. And then I'm going to place it as my transmit antenna. So because the lengths are not identical, it's good to make sure that they are separated correctly. To make sure that the distance are still 1 meter, let's perform a quick measurement to see if I'm at 1 meter. Yes, roughly I'm at the same uh, distance, 1 meter between them. So we can start our measurements. Okay, we have now our left-hand circularly polarized antenna as the transmit antenna, and we haven't touched our receive antenna, which is a right-hand circularly polarized. The distance has been kept the same as these measurements that we have on the screen, and we're going to perform another measurements. So one thing to note here is that you see that this is in fact, I mean, we don't know until we go to the main lobe, but this is lower in terms of the signal level compared to the case that we had the two right-hand circularly polarized antenna. So let it be finished, and then we're gonna compare the maximum signal level of these two acquisitions. So as you see here, this is essentially, if you look at this this case, you see that I have minus 15.73. So when I change the transmit antenna to left-hand circularly polarized, if it was right-hand circularly polarized, it was minus 3.9. So more than 10 dB more, essentially. So I mean, if you remember, in the for linearly polarized antenna, we would rotate our polarization, and we call it cross pole. But for circular polarization, this is in fact our cross pole. So this is essentially the difference between these two are cross pole levels. So in one case, you get minus 3.9. In the other case, you get minus 15.73. So that's one thing to keep in mind, and we can now go to the next step of our experiment. Okay, in this part of the lab, we're going to be measuring the axial ratio of the helical antenna. But before going through the measurement, let me talk a little bit about the method that can be used for performing this type of measurements. And in particular, this is known as polarization pattern method. So the way that it works is that, assume this is, for example, your antenna under test. I mean, the one that I've chosen is linearly polarized, But as you know, nothing is perfectly linearly polarized, or if you have circular polarization, is not perfectly circularly polarized. Everything is, you can think of it as elliptically polarized, but then it goes toward being mainly linearly polarized or circularly polarized. So this is right now the antenna under test that I have. Now imagine I want to measure its polarization. So, and I assume that I want to measure its polarization at this point, so along this axis, so in the far field. So what I'm going to do is that I'm going to take a linearly polarized antenna, for example, like dipole, and when I have this dipole, I'm going to start rotating this dipole right now. So I'm going to rotate the dipole. And as I'm rotating my dipole like this, so you, remember, it's not rotation like this anymore. It's rotation like this. So as I'm rotating my dipole, I'm gonna perform my measurements. For example, right now, this is essentially vertically polarized right now. Look at the feed. You can realize that it's vertically polarized. So if I start my measurement like this, for example, and at this point, you're gonna get almost a null, a zero. And then you're gonna get, if it's perfectly linearly polarized, both of them, then you get zero. Then you rotate it until you get here, so you get maximum signal. Again, you rotate it. Now you get zero. Again, you rotate it. You get maximum signal, and then again you get your zero. So if you now look at the plots that we're gonna have a plot like this. So if that's the angle that we are rotating, so in the very beginning we were here, and we didn't have anything, we had null. And then as we increased our angle, let's call it alpha, for example, then when we got to alpha 90, we got to the maximum. So I'm going to show it that to you one more time here. So that was vertically polarized. That's alpha 0. Now this is alpha 90. So then you get this type of pattern. And as soon as you see that, you say, okay, you have this type of pattern for polarization. Don't confuse that with the donut shape for dipole or loop. So when you see that, then you say, okay, this is linearly polarized. This is an indication that's linearly polarized because at some angle you don't receive anything and then you get to maximum. So that's your linearly polarized antenna. But now imagine you would have a circularly polarized antenna, like helical antenna, for example. Let me go and grab a helical antenna. Okay, so I have now my helical antenna. So this is my helical antenna right now. And then again, I'm gonna have, for example, a linearly polarized antenna. So now, if this is perfectly circularly polarized, if it's perfectly circularly polarized, now if I start like that, I'm gonna receive a signal. And if I start rotating it, my signal will be the same, identical. So if it's perfectly circularly polarized along this axis, then essentially I'm gonna have a perfect, the same measurements as I'm rotating. So if that's the case, then what would be the shape of this pattern that you get? It would be like a perfect circle, because as you, so this is, assume it's a perfect circle. So if this is A, this is A2, this is A, this is A2, the same radius. So then that's the situation that you're gonna have with this type of measurement. So you essentially get the same thing. And then what would be the axial ratio? Axial ratio would essentially be the major axis to minor axis, A divided by A. You're gonna essentially get 1. That's like a perfectly circularly polarized. For linearly polarized, you essentially gonna go to infinity with your axial ratio, because as you see, one of them is gonna go to 0. So that's why you get infinity in this case. Now, If you don't have perfectly circularly polarized, now imagine I have an antenna that's not perfectly circularly polarized, then of course you're not going to get axial ratio equal to 1. For example, for this type of antenna, you get something that's close to 1. It's not exactly 1. It's going to be something close to 1. So because it's not perfectly circularly polarized. And remember, this is only at the best direction. So if you get a different type of antenna, for example, you might get something like you might get a curve something like this. So that this would be the type of measurements that you might get. And if you get a measurement like this, then you might immediately have an ellipse here. And then based on this ellipse, you can actually calculate the axial ratio. Let's call this OAOB. Then your axial ratio would be OA divided by OB. And you can also calculate the tilt angle and other things like that. So essentially, this is our, uh, I mean, you can think of many antennas as like that. And then as they get closer and closer to circular polarization, they become like this. As they get closer to linear polarization, they would get something like this. So that's essentially what we have. So if we want to have our polarization measurements, axial ratio measurements, what we need is essentially a linearly polarized antenna that we can rotate it. So we don't have this ability with this system to constantly rotate this antenna and perform measurements. So what we're gonna do would be, instead of dipole, we're gonna use a horn antenna. Our dipole, if you remember, works at 1 gigahertz. But this horn antenna is the same frequency as the helical antenna. So we're gonna perform one measurement like this, and then we're gonna rotate it 90 degree. That would be another measurements. And for the third measurements, we're gonna this time rotate our uh, helical antenna 45 degrees and perform 3 measurements instead of many measurements on this curve. And then we're gonna get the maximum one, and we're gonna get the minimum of these 3 measurements, and then we're gonna perform OA divided by OB. OA would be the maximum signal that we have. OB would be the minimum signal that we have. So remember, these are many points, and then you do this division between the maximum to minimum. But what we do would be essentially perform 3 measurements, and lab volt manual called that signal 1, signal 2, signal 3. You get the maximum of these 3 measurements, and then you get the minimum of these 3 measurements, and then you can find the axial ratio. Once you find the axial ratio, then you can compare it with the formula that we have for the axial ratio for the helical antenna and see how close they are to each other. If you remember, that formula is based on the number of turns of the helical antenna. Okay, we would like to perform our axial ratio measurements. As I explained in the previous video, ideally we need to have a linearly polarized antenna that's rotating like this. As you see, we don't have a motor to rotate this antenna like that. So what we do, this is our linearly polarized antenna, which is stationary. It does not rotate. So we're going to manually rotate that. But of course, we cannot have many angles. So the way that lab volt manual suggests, and we're going to follow that, is to perform 3 measurements. One measurement like that. Second measurement, we're going to rotate the linearly polarized antenna 90 degree, perform the measurements. Third measurements, we're going to rotate this antenna under test 45 degrees, perform another measurement. So now we have only 3 points, and the points correspond to maximum signal level of each pattern. And then we're gonna use that to calculate our axial ratio. So let's go and start our measurements. You've seen that several times, so I'm not gonna show the measurements to you. We're gonna go directly to lab volt antenna data acquisition and management software. Okay, so I have now our horn antenna mounted and our helical right-hand circularly polarized helical antenna also mounted. They're separated, and the other thing is that lab work manual suggests that the signal level in this experiment be around -5 dB. So to achieve that, I already adjusted the attenuation level corresponding to the separation between the antenna so that I get roughly -5 dB. That's why you're gonna see a different attenuation level here. So if I start my measurements, let's see what type of pattern I'm gonna get. And something to keep in mind is that for this type of axial ratio measurement, we really don't need don't need our we really don't need to have complete pattern measurement. We essentially, the only thing we need is the maximum signal level. But instead of adjusting my maximum signal level, I decided to just perform a complete measurements. So let me store this, and just to be consistent, I'm just gonna also set the maximum signal level to 0 degrees. So that's what I have, and what's relevant to us is this maximum signal level, which is -3.89. Now what I'm gonna do, I'm gonna go and rotate the transmit antenna, the horn antenna, 90 degree, and we perform this measurement again. Okay, I just rotated the transmit antenna 90 degree. So let's start our second data acquisition. And so remember, if it was like a perfect scenario, this horn antenna or linearly polarized, for example, dipole at this frequency would rotate constantly. Uh, so we get so many data points, but here we just go to 90 degree for now. And we're gonna have our second measurement, and we need to pay attention to the maximum signal level. So I can store this too, and to be consistent, let's rotate this so that the maximum signal level is 0. So in this case, I get -3.95. So imagine -3.85, then -3.95. So as you see, this is very good. And something that you may want to compare, you cannot compare the maximum signal level to our initial measurement that we did here, for which we have -6.28. One reason that you can't do that completely is that the attenuation level is different. In the original measurement, the attenuation level was 18 dB. Here is 15 dB. So if we just consider 15 versus 18, you need to add 3 dB loss to all of these, and then you get to this. Something that I wish I would have been more consistent is that the E here is essentially the H here, and the H here is the E here. That's not important, but I'm just telling you, if you look at the right column and you see inconsistency, that's essentially my mistake of not being consistent. So here, for example, this 24.76 degrees that you have should be compared to this 26 degrees. So we have about 1 degree difference between the two measurements. Ideally, they should be identical. And here I have 21, and here I have 22.89. So in this plane is about 2 degrees. But Also the distance, I tried to be 1.5 meter, but it's not exactly the same, and the environment is not exactly the same. For example, right now I probably have my camera stand closer to the receive antenna compared to the previous case. Anyways, but here I'm not going to worry too much about details because the only thing that I want is essentially this maximum signal level. Now, in the last measurements, I'm going to go and rotate the receive antenna. My right hand circularly polarized 45 degrees, and I'm not going to touch the transmit antenna in this case. So I'm going to go and rotate it 45 and then perform another measurements. Okay, I tried my best to do 45 degrees. I cannot be 100% sure if it's exactly 45 or not, but we can treat it as a different data points even if it's not 45 degree exactly. So let's perform our last measurements here and see what sort of maximum signal level we're gonna get in this case. So then at the end of these measurements, we're gonna have three maximum signal level. We're gonna choose the maximum one and the minimum one. So axial ratio is the major axis divided by minor axis, but remember these values that we have are in dB. So if we are dividing, then in this case, because it's dB, we need to subtract. So that would be the maximum of these three values minus the minimum of these three values. So I can store this using a new data so that we have it. So let me complete my save process. So yes, I have them here now, and so if I want to just show you the stuff that's relevant, would be the maximum signal level for this, for this, for this. And let's see what we have right now in terms of maximum signal level. We have minus 3.89, we have minus 3.95, and then we have minus 4.7, the last measurement. Now, which one is the maximum? Of course, minus 3.89 is the maximum that we have. That's our maximum. And which one is our minimum? Is the minus 4.7 is our minimum that we have. So then you essentially end up saying maximum minus minimum. So you essentially need to calculate that, the maximum minus 3.89 minus 4.7, and you get your axial ratio, and then you're going to compare it with the equation that we have for the axial ratio in this case, and then explain your result.